Alright, little owl eyes now blocking one of the interfering beams. Interference pattern goes away. I'm blocking. Get it. So.
And then what's going on here, Mickey?
This is my little 1 hertz interference demo. Oh, I can show you a sound. Oh, here, check this out. Let me show you this. So you may have seen a similar demonstration with sound waves. So the idea is if you take 2 tuning forks that are tuned to exactly the same frequency and beat them together, you hear one continuous sound wave, right? Mm-hmm. However, if you slightly detune one, make it oscillate a little bit slower, now when I beat 2,
get some beats.
Get some beats, right? Problem is, it's really hard to do with light waves because light oscillates much, much faster. These sound waves oscillate maybe 100 hertz, or I don't know perfect pitch, but somewhere in the a few hundred hertz range. And so like getting a 1 hertz difference at a few hundred hertz, not that difficult. Light waves oscillate like 10 to the 14 hertz, 100 terahertz. And so getting a 1 hertz difference between 2 waves oscillating at 100 terahertz is much more difficult. But we can do it. We can get around that by using this interferometer configuration. So you shine a laser. This is just a regular Heine laser, kind of similar to any laser pointer that you'd buy. Mm-hmm. Similar properties. You split it through a beam splitter like this. Half the beam goes this way, half the beam goes this way, and then we send them through 2 acousto-optic modulators. And the acousto-optic modulator is just basically a little crystal that you send a traveling sound wave through. You hook up basically an electric plate that gets driven by a radio frequency electric field, and that jiggles it at a rate that causes traveling pressure waves through the crystal. And now if you have traveling pressure waves, you get alternating areas of high and low index of refraction, makes basically a moving diffraction grating, which causes one spot to become multiple spots. And maybe you can see those multiple spots. It's kind of hard to see, but you can kind of see it. And so these spots are spatially separated and also frequency separated because it's diffraction off a moving diffraction grating. And then the only thing left to do is we set this frequency to be 80 megahertz. We set this frequency to be 8 megahertz plus 2 hertz. And now when you recombine the beams, you have 2 beams that are combined at a 2 hertz frequency difference. And just like the sound waves, which beat at a frequency difference of a few hertz, these light waves will now beat at a frequency difference exactly equal to the frequency difference between their component beams. So that's how it works. Pretty cool, right?
Very cool.
Yes.